morning, everyone. How did the homework go? Any questions? Okay, so before we start our new section, okay, number 32. Okay. All right, so let's look at that. So we have the following sequence: 3 to the n over 3 to the n plus 4 to the n. Okay, and the question is find the limit as n tends to infinity of this expression. Okay, so what happened when n goes to infinity? All right, so ideas. How did you guys do that? So obviously the numerator goes to infinity in this case, the denominator goes to infinity, we know that. So ideas, how shall we find the limit of this expression, of this sequence?
Can't you just make the denominator 3 plus 4 to the nth power?
No, 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 no. Why? No.
Oh, wait, no, you can't. Yeah.
No, you cannot split if you have, I mean, simple. 3 plus 4 squared is not 3 squared plus 4 squared, right? Am I right? This is 7, so we cannot split. We cannot split if you have 2 power. So you have to be very, very careful. Like the 3 plus 4 power squared, basically, if you have a plus b squared, this is a squared plus b squared plus 2 times ab. That's the rule. So we cannot split that. Any other ideas?
L'Hopital's rule.
L'Hopital's rule. Okay, let's see what we get with L'Hopital's rule. So we're gonna try your ideas till we find the right one. So let us see L'Hopital's rule. Okay, it's the derivative of the numerator. What's the derivative of the numerator? 3 to the n. So basically we pretend it's 3 to the x. Now what's the derivative of 3 to the x? We did it, I tried to remind you yesterday. Do you remember? All of you.
Isn't it something like 3 to the n, ln 3 to the n or something like that?
It's ln of 3 times 3 to the x.
Okay.
Okay, so let me try this. I don't know if it's going to work or not. Sometimes it goes around itself, L'Hopital's rule. So this is going to be 3 to the n. So we pretend it's basically x. So down here, it would be the same. Plus, now this is the base is 4. So that's ln of 4 times 4 to the n. Okay, so what we have to do. Now when n goes to infinity, I'm having the same issue. Infinity over infinity. What shall we do? Please, everybody, those who did it, just give me an idea, how did you do it? Because remember, you have to show all your work, you have to do it algebraically all the time. So anybody, what am I supposed to do now? If I apply L'Hopital's rule again, what do you think is going to happen?
Couldn't we just cancel out the ln of 3 from each top and bottom?
Not, because this is ln of 3, this is ln of 3, this is ln of 4. I cannot, the only way we can simplify if we can factor. I cannot factor ln of 3. Anybody? Please, all of you, pitch in. So if I apply L'Hopital's rule again, if I apply L'Hopital's rule again, what do you think is going to happen? Are we going to improve? Is it going to help us? Usually, the idea is to help us, to get rid of infinity over infinity. If I apply it again, I'm not going to go anywhere, because if I apply it again, I will have ln of 3 times ln of 3, 3 to the n. I still am stuck with that, the same term. Here I will have ln of 3 times ln of 3, 3 to the n, ln of 4 times ln of 4 times 4 to the n. So in this particular problem, this L'Hopital's rule is going to fail. So we have to find another approach. Okay, so another approach. All right, one of your classmates is suggesting divide, which is actually the best approach, divide by 3 to the n numerator denominator. So we're going to divide, basically to get rid of this infinity over infinity, we're going to divide by 3 to the n numerator and denominator. Because this first one, L'Hopital's really didn't really get me anywhere. Another nice approach is divide. I mean, I see 3 to the n, 3 to the n, we're going to divide by them. What do we get? So the idea is divide. So we're going to divide this by 3 to the n, the numerator. We're going to divide this by 3 to the n, and this by 3 to the n. All right, and see what do we get from that. We're going to get the limit as n tends to infinity of. This is a 1 in here. And then I'm going to have a 1 plus 4 to the n over 3 to the n. Now, what happened here? What's the limit of this expression?
Isn't it, since the 4 to the n is over the 3 to the n, that's something that's infinity, and since it's 1 over something large, then that isn't it 0?
Why is this large?
Oh wait, no, I'm sorry. No, I thought it was just regular 4 over 3 to the n.
Ah, yeah. Why is this large? What did we do yesterday? That's 4 to the n over 3 to n. How can we write this? 4/3 to the power n. And now, when n goes to infinity, what's the limit of 4 over 3 to the power n as n goes to infinity? That's the type of limit we saw yesterday. This is equal to what? Please, all of you, wake up. What's this limit? When n goes to infinity, what happened to 4 over 3 to the power n? What's the limit of that?
Goes to infinity as well.
Infinity, because, exactly, it's infinity because 4/3 is bigger than 1. And remember what we saw yesterday? What we saw yesterday is that, so what we saw yesterday, that if r is bigger than 1, the ratio is bigger than 1, then the limit of r to the n is plus infinity. Okay, so now I am basically fine. This is going to blow up to infinity. And then I have 1 over infinity, something large, and now I'm going to get my 0. Absolutely step by step. Okay. So again, we had to be a little bit creative. L'Hopital's rule did not get us far in this particular problem. It does great job in a lot of problems. It didn't in this particular one. So the idea is that to get rid of this infinity over infinity, because we saw we have the same term, so we divided by it. And that's what your classmate suggested. By dividing by it, I don't have infinity over infinity. My problem simplified tiny bit. Then finally, I'm done with here. And when I got here, we just use what we've learned yesterday. Okay. Right, now suppose I'll give you one more problem along the same line. So let us see what we saw yesterday, the idea of r to the n, before I move on. So if r in absolute value is less than 1, then we know that the limit is equal to 0. Because as we said, when you take a number, if the number is less than 1, as you raise it to higher and higher power, the number gets smaller and smaller. And if r bigger than 1, the Rn is infinity. R less than -1, the series the sequence diverges. So that's what we saw yesterday. So one more problem, and you get 2 minutes to do it, and then I proceed. So it's problem from the book. It's like number 30 in the book. Actually, not number 30. Let me pick another one. Let's see number 28. but 30 is like the one I did. Suppose I have a following sequence. Okay, so and the question is, what's the limit as n tends to infinity of this expression, of this sequence? It means when I start plugging in n large, what do I get? Quickly. Quickly, what's the answer? You should not have, this should not take you too long to do that. Okay, anybody? 0, because. Immediately 0, because. This is r to the n, where r, this is your r here. So here the r is minus 0.03. In absolute value, the r is less than 1. It means the limit of minus 0.03 to the power n is going to be equal to 0. Again, it's a number. Those, because I have a minus, this is the picture where the number is going to be positive, negative, but it's heading toward 0. Because now number 27, again, I will do that. So 2 to the n plus 1 times 3 to the minus n. Okay, and the question is, find the limit as n tends to infinity of this sequence. Again, I did that yesterday. I want to know. And remember, if you give me an answer without explanation, I won't give you credit. So it has to be explained clearly.
Two n plus 1 can become 2n times 2.
Yeah, that's what, yeah, this we did yesterday. Very good. And then?
And then 3 to the negative n could probably become 3n times, never mind.
Okay, anybody else? Please, all of you pitch in.
Could the 3 to the negative n become 1/3 to
Right,
n
right.
power?
It become 1/3 to the n. Okay, because I don't know what to do with it. It's minus n. Now proceed. You guys have everything in front of you. What you're gonna get?
Can you take out that 2 and put it in the front? Is a constant that bringing the 2?
This is not gonna affect anything. And then what you want me to write?
Let's say 2/3 to the n power.
Right, and then become 2/3 to the n power. And then everything is clear. All right.
Zero.
Yeah, now it's become 0. Why it's 0? Now it's clear. Now I don't have any doubt in my mind. This is going to be 0 because this 2/3 here is less than 1. So this term will go to 0 times 2 will become 0. Okay. So that's how we're going to manipulate those type of expression. All right. Okay, so today we're going to move to the following section, 11.3 basically, no 10, I think we are in 10. So it's actually going to be a little bit of 10.1 and 10.3. Okay, so we're going to start the idea of infinite series, which is what this whole chapter and the following one is about. So infinite series. Okay, so far we defined sequence. Okay, and sequence. Sorry, Israel, I did not read your question. Can you say just 0 off the back because there is no 1. There is no 1 here. Yeah, this goes to 0. You're right. But this one goes to infinity. Infinity times 0 is indeterminate. So your classmate tell me, can I say immediately 0? My answer is no. This is infinity, and this goes to 0. Infinity times 0 is indeterminate, so it could be either one. So let us say I flip the scenario. Suppose I have 3 to the n times 1/2 to the n. Suppose I have this kind of sequence. Look what happened. This goes to 0, but this goes to infinity. But the product will be 3/2 to the power 10. It's not going to be 0. This is going to go to infinity because then the r will be bigger than 1. Okay, so we have to be very careful. We have to be very careful. All right. Yeah. Yes, Freddie. That's what we did. All right. So infinite series. For recall a sequence. A sequence is a list of numbers. No more, no less. It's just a sequence. You know, when we talk about sequence, it's just a bunch of numbers. 1/2, 1/2 square, 1/2 cube. Just a list. Nothing deeper than that. A series is going to be the following. We start with a sequence, and then we're going to start adding them, and so on and so forth. And the question is becoming, what does it mean to add infinitely many terms? Okay, so that's really the idea. So we start with a sequence. A sequence is a list, just a list. So suppose we have a sequence. So suppose we have a sequence AN. So AN. It means a sequence, it means a list. A1, A2, A3, etc. Okay, then we're going to add the term. We add the term. There is an addition involved. We add the term of the sequence. We add the term. So we get, for example, A1 plus A2 plus A3 plus A4, etc. We keep adding the term. This sum is called infinite series. It's called infinite series. So the sum, because it's an infinite sum, we give it a name and we call it infinite series, and we denote it by. Whenever we have a sum, we use a sigma notation for it. So it's denoted by sigma, which means the sum. A sub k, k is those 1, 2, 3, where k, according to ours, goes from 1, that's the first term, all the way to infinity, because we never stop the term. And this is mean A1 plus A2 plus A3 plus so on. We never stop. So now the big question is, what does it mean? So the question is, what does it mean to add infinitely many terms? What do we mean by that? And that's really the goal of today's section and this whole chapter. What does it mean to add infinitely many terms? Okay, that's really the idea. So I'm writing this stuff up, but what does it mean? All right, so we're going to elaborate first by an example, and then we're going to proceed. So let us consider the following example. Suppose I'm going to add the following. A half plus 1/2 square plus 1/2 to the power 3 plus 1/2 to the power 4, etc. Suppose I take this infinite series, which is in sigma notation become sigma. So we're adding terms of the form 1/2 to the k, where my k go from 1 all the way to infinity. Okay, and the question, what does this sum mean? The meaning we're going to give to the sum is the following. We're first going to we're going to construct the following. I'm going to say, let S1 be the first term, 1/2, big deal. And then I'm going to take S2. What I'm going to do now is I'm going to add the first 2 terms. That's going to be the idea. Then I'm going to add the first 3 terms. Then I'm going to add the first 4 terms. That's what I'm going to do exactly. And I'm going to keep adding the terms, more and more terms. Now, the question is going to be, all right, as I add more and more terms, what's going to happen to those sum of those terms? That's what we will be looking for. So first I take S1 to be 1/2. Then I'm going to compute S2. S2 is the sum of the first two terms. Sum of first two terms. Okay, so that's S2. So S2 is equal to a half plus 1 over 2 squared. I'm going to add them. So this is going to be equal. If I add those, I will get a half plus 1 over 4. And I find a common denominator, which is going to give me a 2 plus 1. I get 3/4. That's the sum of the first two terms. Then I'm going to compute S3. S3 is the sum of the first three terms. So I'm going to take a half. I'm going to take 1 over 2 squared, and I'm going to add to it 1 over 2 to the power 3. So I'm going to add the first three terms and see what I'm going to get. Now, I've already done those prior. I did that here. So this is going to give me 3 over 4 plus 1 over 8, okay, which is going to be equal to. So if this is a common denominator is 8, 2 times 3, that's plus 1. So this is going to give me 7 over 8. Okay. Then I'm going to be patient. I'm going to compute S4, the sum of the first four terms. So it's a half. As you realize, I'm writing them very patiently because I wanted to know exactly what we are doing. We're just adding those terms and see what happens. So those I've already taken care of. This is 7 over 8. And this is 1 over 16, basically. So I'm going to end up with 16 down here. 2 times 7, we're going to get 15 over 16. Okay. So I'm adding. So this is my S1 here, my S2. This is my S3. This is my S4. Now I'm going to compute my S5. And at some point, you tell me you should scream and tell me stop. We see something. Okay, what's S5? Means I'm going to add a half plus this. So I'm going to keep adding the terms and see where we're heading. Plus 1 over 2 to the power 5. Again, this I had taken care of. So this gives me 15 over 16. And this is going to give me 1 over 32. Now, again, this is twice that much. That's the pattern is becoming. Then I will have this 2 times 15. That's 30 plus 1, 31 over 32. Okay. If we watch carefully, there is a certain pattern that is trying to show up. Can anybody see the pattern?
We're getting closer and closer to 1.
Yeah, what is the pattern? So for example, if I add the first 100 terms, what do you think is going to be the answer? Can anybody see a certain pattern?
It looks like the numerator is getting multiplied by 2 plus 1, and then the denominator is getting multiplied by 2, I guess. Like 15 times 2 is 30, plus 1, you get 31, and then the denominator is 16, multiplied by 2, you get 32.
From here to here, you mean? From here to here?
Yeah, from 1 to 1 before.
Okay,
like,
very good. Okay, so let us build a pattern out of that. Okay, how we're going to do it. So the first one is this multiplied by 2. So this one is 4, or let us say 2 squared, because that's going to be easier for a pattern, right?
Yeah.
This is going to be, you multiply this by 2. 2 cubed, correct?
Mm-hmm.
This one is 2 to the power 4. So I'm keeping the whole picture in front of you so you guys start building up the pattern. This is 2 to the power 5, and this is 31. Okay, now who can give me S100? Following the pattern. So the pattern suggests the following. Anybody? I know that I have one answer, which is a correct answer. What's the denominator? S5, 2 to the 5. S4, 2 to the 4. So this should be 2 to the 100. And the numerator is 1 less than the denominator, 31, 32, 15, 6. So it's going to be 2 to the 100, basically minus 1. So that's really what the pattern is suggesting. But as your classmate just said, what do we notice? What we notice is that the sum, we notice that as we add more terms, those sums, S1, S2, S4, those sums that we're going to give them a special name, S1, S2, F3, S4, etc., those sums are becoming close to 1. Okay, so as we add more terms, those sums, this is what I'm looking at now, the sums are becoming close to 1, because 2 to the power 100 minus 1 over 2 to the power 100, this is really almost 1, actually, are becoming close and closer to 1. So what we're going to write, which is very reasonable, so to write the following. So what we're going to write is the following, which make a lot of sense right now. That if we take a half plus 1 over 2 squared plus 1 over 2 cubed plus etc., this sum is equal to 1. Or we're going to write sigma. So I always write things as a sigma notation and without sigma notation, at least at the beginning. So k equal 1 to infinity is equal to 1. Okay, so let us a little bit recap what we did here. So what does it mean to say this is equal to 1? What are we doing? What we are doing is simply start adding the sum of the terms and ask ourselves, as we add more and more terms, what are we going to head to? So from this problem, we realize the more we add, even though we're adding infinitely many, but the sum is really approaching 1. So we're going to say that the sigma is equal to 1. Now those sums, S2, F3, S4, we are going to give them a special name and we are going to call them partial sums. So those sums, S1, S2, the sequence of those sums, we're going to give them a special name. We're going to call them partial sums. So now my first definition to formalize this. Okay, so definitions. Okay. All right, so definition of partial sums. First. So definition of partial sums. Okay. Right. To every infinite series. So whenever we have a sum, we're going to associate, so to every infinite series, sigma ak, k equal, k can start at 1 to infinity, it starts at 0. This is not be an issue. So to every infinite series, we're going to associate the following. I'm going to associate the following sum. So we associate the sequence. Okay, so to every infinite series, we will associate the following sequence. S1 equal A1. S2 is A1 plus A2, the sum of the first two terms. F3, A1 plus A2 plus A3, etc. Sn is A1, so the first all the way to An. So it's a finite sum. Then as the sequence Sn, so S1, S2, Sn is called the sequence of partial sums. Of partial sums. Okay, so this sequence Sn, when we start adding, we're gonna get a bunch of numbers. This list is called the sequence of partial sums. Now, if we have this series, we will say that the series converges if the sequence of partial sums itself converges. And we're going to say that the series diverges if the sequence of partial sums diverges. So now, definition of convergence of and divergence of an infinite series. Part 2. Now, so we have two things. We have the sequence an and we have the sequence of partial sum. Now, if the sequence Sn, in the sequence of partial sums, converges to a limit S. So if the sequence of partial sums, sorry. Sorry about the pencil, I wasn't paying attention. All right. So if the series of partial sum converge to a limit S, then we say that is, if the limit as n tends to infinity of the partial sums equal to S, then we say that the series or the infinite series sigma ak converges. So if the partial sum converge, and we write so if the partial sum converge, we say that the series converge, and we write sigma ak means a1 plus a2 plus a3 plus etc. is equal to S. So the value of the sum of this infinite sum is actually the limit of the sequence of partial sum. If the sequence Sn diverges, the sequence of partial sum diverges, it means the limit goes to infinity or the limit does not exist, then we say that the series diverges. Diverges. Okay, so a series converge, this infinite sum converge if the sequence of partial sum converge. So what does it mean for a series to converge? It converges if those sums themselves converge. That's really what the meaning we are going to give to this infinite series. So in other words, can I move on? So if you see somebody writing, so when we write something like that, A1 plus A2 plus A3 plus A4, when we write that something like that is equal to S, what we actually mean is by adding sufficiently many terms, our sum is going to become closer and closer to S. So when we write something like this, it means when we add sufficiently many terms, we get close. When we add sufficiently many terms, the sum of the series, we get close to S. So if we add sufficiently many terms of the series, we get close to S. That's really, yes.
So is there like a set amount of numbers that we should add, or is it just
no way? It's like no, it's a sequence. When you have a sequence, when the sequence that I say converges to 1, it means when n becomes large, the terms become close to 1. It doesn't mean the 100th term become close to 1. It could be the 1,000th terms. It depends how fast it gets close to 1.
Okay.
And it's the same thing here. You kept adding terms till you realize that those terms are becoming close to a fixed number. And this is the number that will be the S. But I cannot tell you the first 100. Sometimes you need the first 1 million term, to be honest with you, to get close to something. And sometimes the first 10 terms will get you almost the actual value or very close to it. So I cannot, that's when we say it converges fast or it converges slow. That's what's going to happen. And we will try to take examples. So aside on the note, so suppose that I say you don't have to write everything. Suppose I tell you that 1 plus 1 over 3 plus 1 over 3 squared, which is something very soon you guys will know it. So suppose I tell you this is equal to 3/2. Basically what I am talking about, what does this blah, blah, blah plus dot, dot, dot equal to 3/2? It means that if you pick up your calculator basically, and you start adding, physically adding those finite sum, you realize that at some point you're getting close to 3/2. That's really what it means. That's what this sum is equal to 3/2. So today we're going to consider, because we really don't have a lot to work with, we're going to consider two series, okay, and we're going to try to decide if they converge or not. So the first one is going to be very simple, but we have to, that's what we can start with, something simple. So question is, let us consider the following series. So example number 1. Okay. Sigma n equal 1 to infinity of, k equal 1 to infinity of k. All right, what does this mean? What does it mean, this sum? First, this is me, what are we adding? K equal to 1 is a 1, plus k equal to 2, 2, plus k equal to 3, 3. That's what does it mean? Plus 4, plus 5. Okay, that's what this means. Very simple series. So question number 1 is find S1, S2. It means here I'm after the partial sum. F3 and S4. When I'm asking you those, it means I'm after the partial sums. All right. S1 is the first term. S2 is basically 1 plus 2, which is equal to 3. S4 is 1 plus 2 plus 3, which is equal to 6. And so on and so forth. So S4 is, sorry.
Okay, yeah.
S4 is 1 plus 2 plus 3 plus 4. Means 6 plus 4, this is equal to 10. So question number 2, does the series converge or diverge? What do you think?
Diverges.
Because
there's no like set area where it's going, it's just going to infinity.
right. As we add more term, it's clear here that those terms, because this is a simple example. So does the series converge or diverge? Okay, in this particular scenario, which is very simple scenario, okay, it's very clear that the series, so here it's clear that the partial sum, the Sn, goes to infinity. So that's what I actually looked at. I looked at the Sn goes to infinity, so the series diverges. Okay. Example number 2, a little bit more subtle than that, but that's really what we are after. We're really after those. So example number 2 is the following. I will consider the series sigma n k equal 1 to infinity of 1 over k times k plus 1. Okay, that's really my series. And the question, does this converge or diverge? And what is the sum? I mean, what's the sum? So my first question is that finding the sum, or whether series converge or diverge, I have to go after the partial sums. So I'm going to go after the partial sums and see if there a pattern. Is there something I can do with them and see what happened to them? So question number one is to evaluate the partial sums. But before I do that, let us a little bit understand this notation. Let us understand it. Okay, it's equal to what? If k is 1, I will have 1 over, I plug in 1 in here, I will have 1 over 2. Plus, if k is 2, I will have 2 times 3, or 6, of course. Plus, if k is 3, I will have 3 times 4. Now it's easy for us, 4 times 5, and so on. So it's nice to see what the pattern by writing clearly the first few terms. So now question number one is find S1, the partial sums. I want S1. Basically, I want a pattern. So I'm going to find the first, and then I'm going to ask you, do you see any pattern for the sum? All right. So let's do that. What is S1? S1 is a half. That's the first term. What is S2? S2 is the sum. Means it's a half plus 1 over 2 times 3. Means, of course, this is a half plus 1 over 6. Now, common denominator is 6. So I will have a 3 in here plus 1. It's 4 over 6. If I reduce it to a lowest term, we get 2/3. So that's S2. So I have to keep, I'm going to keep finding sums till I see a pattern, which is not always. We will never be able to see it easily, except with a simple example like the one I'm giving today. So S3 is, again, a half plus 1 over 2 times 3 plus 1 over 3 times 4 equal to. Now, the first 3, we know them. So it's a 2/3 plus 1 over 12. Okay. And then 12 and 3, that's going to give me a 4 here. 8 plus 1, 9. So I'm getting 9 over 12. And then I will have 3 and I will have 4. Okay. So something is already showing up, but I cannot trust the first few terms. I will keep going. It's going to be a half plus 1 over 2 times 3 plus 1 over 4 times 5, I guess. Again, I already taken care of those. That's 3 over 4 plus 1 over 20. Common denominator 20. 20 into 4, that's going to give me 5 times 3. That's going to give me 15 plus 1. That's going to give me a 16. And now if I simplify by dividing by 4, I will get a 4 in here, and I will get a 5 right here. So is a pattern emerging? What do you think? Anybody see any pattern emerging?
They're getting closer and closer to 1.
Yeah, because can anybody give me a general formula? So S5 is going to be what? What's S5?
5/6.
5 over 6. It has to be 5 over 6. Let's see if it's correct. So if I'm going to add, so remember, I'm adding on purpose. I'm boring you with addition because I wanted to know that that's what we're doing. We're adding finitely many terms and see what's happening. So this is 5. So that's 6 times 7. 5 times 6. I already did that. That's 4 over 5 plus 1 over 30, which will give me a 30 in here. 30 into 5, 6 times 4, that's going to give me a 25 in here. Again, we're dividing by, so I'm going to get if divide by 5, I will get 5 over 6. So of course, something is going on. So my question B is, use the pattern to find a formula for Sn. For Sn. It means, what's the general formula? So instead, like S100. So find the formula for Sn. So in general, it means if I add the first n terms, what's going to be the formula for Sn? Using the pattern we developed, what's going to be Sn?
N over n plus 1.
It's very clear. N as 5, 5 over 6. N over n plus 1. Means if I add the first 100 terms, I'm going to get 100 over 101. I add the first 1,000 terms, it's 1,000 over 1,001, and so on and so forth. Now, the last question is, does the series converge? And if it does, find its value. Okay, so the last question is, what can we say about the series itself? Does the series converge? What can we say? Okay, so does the series converge, and find its sum? And if so, find its sum. Find the sum. Okay, so now what is the series? The series is, so sigma 1 over k times k plus 1, k equal 1 to infinity, is nothing more than the limit as n goes to infinity of those partial sum. So that's really what this series is. It's what happened to the partial sum when n goes to infinity. So in my problem here, so it's the limit as n tends to infinity of n over n plus 1. So we're doing it a little bit in a more rigorous way. But this is equal to what? When n goes to infinity, n over n plus 1, this is just a simple sequence. The limit of that, if we divide by, you just look at it, if you divide by 1 both sides, it's going to give me 1 over 1 plus 1 over n. This is equal to 1. So this tells me that this sigma, this sum, is equal to 1. Okay. So this sum equal to 1, which means exactly writing this equal to 1, it means what I'm telling you is that those partial sums, those sums are close to 1. So as we add more and more and more terms, those terms are becoming close to 1. So the sum of the series is equal to 1. So the sum of the series is the limit of the partial sums, of the sequence of partial sums when n becoming very large. Okay. Now, finding two things. Finding if the value of the sum is a tremendously hard problem, except in the simple one that I'm giving you. So what we're going to do tomorrow is, again, work with simple series that we can find the sum. And after that, what you will be doing is, since it will be hard to find the sum, extremely hard to find the actual value, what we will be concentrating on is the following, is ask ourselves, does it converge or diverge? It means, do the sum get somewhere or not without having to evaluate the sum? So that's really how we'll be moving. So tomorrow we're going to take easy series and we're going to find their sum. After that, we're going to develop ideas. Okay, how can I tell if it converges without having to find the sum? Because finding the sum would be a very hard problem. Okay, so at the end, I'm going to talk a little bit about notation for a series. So a few words about notation. Suppose I have the following series, sigma, let's say k equal to 1 to infinity of 1 over 2 to the n. Okay, so sorry, 2 to the k. So it's a half plus 1 over 2 squared plus 1 over 2 to power 3 and so on. Now, can we also, so this could be also written as, suppose I want to write it as from 0 to infinity. What shall I do? So the k doesn't have to start from 1 to infinity. It can start from 0 to infinity. So if I'm going to rewrite this, so rewrite it. So I start from 0 to infinity. Who can rewrite it? So this will happen. Okay. Suppose I write this like that. 1 over 2 to the power k plus 1. K equals 0 to infinity. Am I talking about the same sum? Yes or not?
Yes.
Yeah. How do we tell? Just plug in terms. If k is 0, it's a half. If k is 2, square. If k is cube, and so on and so forth. So we can write a series, the notation, in basically different way. We can start at 1. We can start at 0. But to make sure that we're getting the same series, just write up the first few terms. I mean, this one also, I can, for example, I can rewrite it like this also. I can, for example, say 1 over, we won't, but I can do that. 1 over 2 to the k minus 4, where k start from 5 to infinity. I can do something crazy like this. And this will also represent the same series, because if I start plugging in value, I will have a half, I will have 2 squared, and so on and so forth. Okay, so we don't have to start at 1. We can basically start anywhere I want from the bottom, but always is to infinity because we're adding them infinite, just we keep adding them. But the index below can really start anywhere we want. So we can have flexibility in the way we're writing the series. All right, I stop here today. Please do the homework for tomorrow. It's from section 10.1 because this is more relevant to 10.1. And tomorrow we take 10.3. Okay, class is dismissed. Any questions? Stay.